Want to hear a fun fact?
Okay, sure.
Did you know that the water in the toilet bowl spins in an opposite direction in the northern hemisphere than it does in the southern hemisphere?
Really?
Yeah, it spins counterclockwise in the northern hemisphere and it spins clockwise in the southern hemisphere, like hurricanes. This is called the Coriolis effect.
Actually, Caroline, that's not quite right.
Stop right there. So what is the Coriolis effect? Here's two students from oceanology here to debunk my myth.
So the phenomenon that Caroline just described is called the Coriolis effect. It does play a role in how hurricanes spin in the northern and southern hemisphere, but it almost has nothing to do with how water drains in either hemispheres. To better understand this, let's draw a diagram. So we all understand how the Earth rotates about an axis that runs through the northern and southern poles. Now let's take a city that lies on the equator of Earth. We can calculate how fast the city is spinning using the circumference of Earth, which is 40,030 kilometers, and understanding the fact that Earth makes a full rotation in 24 hours, meaning any city will end up in the same exact spot after 24 hours. So using these two pieces of information, we can calculate the speed at which this city is spinning, which is equal to 40,030 kilometers divided by 24 hours, which gives an average of 1,667 kilometers per hour. Now let's take a second city, say Philadelphia. Philadelphia is located at approximately 40 degrees north of the equator. And if we take the cross section of this latitude, then the circumference of this point is approximately equal to 30,700 kilometers. Using the same logic that we use for the city at the equator, we can calculate the speed at which Philadelphia is rotating at. So doing this math, we see that the speed of Philadelphia is equal to 30,700 kilometers divided by 24 hours, or 1,279 kilometers per hour. Wow, that's way different from how fast this city was spinning at. This difference in how fast either city is spinning at, depending on where you are, latitude-wise, is what causes the Coriolis effect. For example, if we take a theoretical string that runs right from Philadelphia all the way down to this city in the equator, and then we look at how this string moves as the Earth spins, we'll see that the string eventually becomes deflected to the west the more and more the Earth rotates, because this point at the equator is moving much faster than this point in Philadelphia. So these ends are lagging behind. That is why we have the Coriolis effect.
So Nee just explained why we have the Coriolis effect. But now, what's the difference between the Coriolis effect affecting hurricanes versus not affecting the water in the toilet bowl? For that, we're going to have to dive into a little bit of the math. So, we know that the average diameter of a hurricane is equal to 160 kilometers. So, a hurricane on Earth would take up some portion of the Earth's surface. We can calculate this angle by knowing the diameter of the hurricane and the circumference of Earth and multiplying that by 360 degrees. This gives us 1.44 degrees for a hurricane. So this angle is 1.44 degrees. How does this help us? Well, knowing this angle here, we can then calculate at what latitude the northernmost part of the hurricane is versus the southernmost part of the hurricane. Essentially, we can calculate the circumference there versus the circumference there. While me was explaining the first part, I was crunching some math and found that the change in velocity of a point at a different latitude from another point to be equal to 2 times pi times the radius of Earth times by 1 minus cosine theta divided by the time which it takes, which is 24 hours. So using this, and we know our angle here, theta, to be 1.44 degrees, we can calculate a difference in velocity of the northernmost part of the hurricane versus the southernmost part of the hurricane to be 0.5273 kilometers per hour. Translating this into something we can understand better, we know that this is approximately 0.146 meters per second, or a very slow walking pace. So how does this compare to a toilet bowl situation? Now, the toilet bowl diameter is much, much smaller than the diameter of a hurricane, it being approximately 0.25 meters. Here we're looking at kilometers, here we're looking at 0.25 meters, so much smaller. So doing the same calculation as before to calculate our angle, we get a much smaller number, 2.25 times 10 to the negative 6 degrees. Already we can see that this number is a lot smaller than this number. So a point representing the toilet bowl would not have much of a change in latitude between the northernmost versus the southernmost parts of that toilet bowl. So looking at the velocities, we'll see it get even smaller. So the difference in velocity in the toilet bowl water is equal to 1.3 times 10 to the negative 12 kilometers per hour. This is practically zero. And as you can imagine, your toilet bowl sitting on Earth, the water closest to the equator is not moving that much faster than the water farthest from the equator. This explains why the Coriolis affects only hurricanes, but not toilet bowl water. It has to do with the scale. The hurricane takes a much larger scale than the small toilet bowl water does. So, as we can see, toilet bowl water will not, the direction toilet bowl water spins does not depend on the hemisphere you're in. But the direction that toilet bowl water does spin in can be affected by things such as toilet bowl shape or the direction that the water is shot at. So, myth debunked.